let's talk about a slightly new thing. But it's actually going to be based on something we just did. I want you to observe something. We're going to start studying for a moment, for example, this block of code. So if you can just take several instructions in a row and be like, these several instructions in a row, they're like a subroutine. There's like a composite instruction. Like I could bundle it up into like a package and, whenever I want, I could do double Hadamard. So it's like subroutines. And some this way, we get like new instructions or new physical things that we can do out of old physical things that we could do. So we're going to talk about that a little bit. But one thing I want to mention right now is, this particular one, what did we just learn from these 4 examples? This particular one we learned, or these last 2 examples, if you start at 0 and do double Hadamard, you get back to 0. And if you start at 1, which we effectively did here, and do double Hadamard, you get back to 1. So actually, we learned how this subroutine, double Hadamard, operates on the 2 possible basic states, 0 and 1. And as I alluded to last time, it's, once you know, we'll see this soon enough. Once you know, we've sort of already seen it. Once you know how like an instruction or a composite instruction or a subroutine operates on all the possible basic states, that defines how it operates on everything. Because really, like when you're eventually like plugging it into like a big old, amplitude tree, you just need to know like what happens on zeros and ones. So, so we could say like, okay, if we make up this kind of new composite instruction, double Hadamard, which operates on 1 qubit and just does, Hadamard. Probably start writing had instead of Hadamard. It's like a new instruction. And remember when we were describing instructions, we kind of was like, oh, you can always write down like the sort of paths diagram for them or the matrix. They're the same thing, paths diagram or a matrix. So we can have a paths diagram or a matrix for this. So what is its paths diagram? Well, we kind of worked it out. So it only operates on 1 qubit. So the incoming possibilities are 0 and 1. The outgoing possibilities are 0 and 1. And we just saw it. 0 goes to 0 with amplitude 1, and 0 goes to 1 with amplitude 0. So we're like, let's not make this too cluttered. We'll just erase this one. And 1 goes to 1, also with amplitude 1. Or if we were to make the matrix for it, let's just arranging these 4 numbers differently. These 1, the 0 that we erased, the other 0 that we never even wrote, and the 1. It's kind of like going like this, to 0 and 1. 0 goes to 0 with amplitude 1, and goes to 1 with amplitude 0. 1 goes to 1 with amplitude 1, and 0. So that's the matrix for double Hadamard. And this is equivalent, or this is the path diagram you would draw for like another instruction, or you might rather name this instruction like no op. This is the instruction that does nothing. So this is like really equivalent to, no op on A. Okay, just nothing changes. And actually what that means is interestingly enough, is that from this you can infer that Hadamard is its own undo. Hadamard is undoable, and the undo of Hadamard is Hadamard. That's exactly, what I mean by this sentence is literally this. If you do it twice in a row, it's equivalent to doing nothing. Okay, so let's do another example like this, just to drive home the phenomenon that any, let's say, qubit manipulation subroutine, let's assume there are no special instructions like new qubit or extract all. You just have like a block of code that has the qubit manipulation instructions. Any such block of code itself could be thought of as a composite instruction, which has its own like paths diagram or matrix. And you could imagine just like shortcutting. Once you knew that, like if you built the tree for this code, you could be like, this is just double Hadamard. And instead of doing 2 layers, I can just like plug this in for like 1 layer. But let's do like a more non-trivial example. So let's work out double clockwise. So for this, you need to remember this like funny clockwise instruction that I invented sort of for illustrative purposes. Okay. So how do you figure out, if you were to think of this as a composite instruction, how do you figure out its path diagrams or its matrix? Well, you just have to figure out what happens if you do this to 0 and what happens if you do this to 1. So, okay. How do you figure out what happens if you do this to 0? Well, it's amplitude trees. You start at 0, and then you're like, okay, like I'm going to do clockwise, and then I'm going to do clockwise again, and we'll just see where we get to. Now you have to remember what clockwise does. I'll tell you. 0 goes to 0 with amplitude 0.8, and it goes to 1 with amplitude minus 0.6. Okay, I told you that last time. And actually, I'm just going to do it on 1 over here at the same time. So sort of alternatively, if I'm going to figure out how does it work if I start at 1, again, this goes to amplitude 0 with, or it goes to 0 with amplitude 0.6, and it goes to 1 with amplitude 0.8. Okay, these 4 numbers are like the definition, actually, of clockwise. You'll see them in the paths diagram for, basically the paths diagram for clockwise looks like this, only you squish these 2 things together and show all 4 amplitudes at once. Okay, so that's the first instruction. Now, okay, let me come back to this. Let's say we're going to do clockwise again. So, all right, you know how this whole amplitude business works. Okay, so if you're at 0, it goes to 0 with amplitude 0.8, goes to 1 with amplitude minus 0.6. If you're at 1, it goes to 0 with amplitude 0.6, and it goes to 1 with amplitude 0.8. Okay, so now we're done, so we still finish. So this is 0.8 times 0.8 is 0.64. 0.8 times minus 0.6 is minus 0.48. Minus 0.6, so this is minus 0.36. This is minus 0.48. And we're still not done because we have to do this sort of collation. So like the final state has amplitude something on 0. And what is this something? Okay, we get to 0 with amplitude 0.64 and also negative 0.36. So those add up to 0.28. And we get to 1 with amplitude negative 0.48 and another negative 0.48. That's negative 0.96. Okay. So double clockwise, when applied to 0, gets you to this state. And I encourage you to check on your calculator that this number squared plus this number squared happens to equal 1. Okay, we can similarly figure out what it does here. If you do double clockwise on starting from 1, try to do it really fast. 0, this is like 0.8, minus 0.6, 0.6, 0.8. This is 0.48, minus 0.36, 0.48, 0.64. So final state, it's amplitude. How much on 0? It's 0.48 and 0.48, so that's 0.96. And on 1, we get minus this, so it's 0.28 on 1. Okay. So this little exercise tells us kind of everything you need to know about double clockwise if you want to now consider it like a new little subroutine that you can plug in. You know what it does to 0, and you know what it does to 1. And therefore, like, you could figure out, you could understand what to do if you're in the middle of like a big amplitude tree that's applying double clockwise, because you only need to know like how it acts on 0 and how it acts on 1 to fill in your amplitude trees. So we could, say, okay, this thing, we finally figured out its paths diagram, which we draw like this. We got 0, we got 1, we got 0, 1, and we just worked it out. So from 0, you go to 0 with 0.28, and you go to 1 with amplitude minus 0.96. And from 1, you go to 0 with amplitude plus 0.96. And 1 goes to 1 with amplitude 0.28. So this is equivalent to a matrix that looks like 0.28, 0.28 minus 0.96, 0.96. That's 0, 1, 0, 1. Okay, so we did it. We sort of figured out, in some sense, we figured out like the definition of double clockwise. Any questions about this? Okay, and let me just, I know this is going to be like kind of calculational, but it's, of course, very good to practice calculations when you're just learning how all these things work. So I'm going to do another, I'm going to continue this in a bit of a calculational way. So, you know, I might ask you the following calculational question. Say you had two qubits, A and B, and somehow you got them to this superposition state. Somehow you read some code, and yada, 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 you ended up with 0.5 amplitude on 0, 0. And let me just make sure I do my exact example. Minus 0.5 amplitude on 0, 1. Minus 0.5 amplitude on 1, 0. And positive 0.5 amplitude on 1, 1. Okay? And this is possible because like the squares of these numbers are quarter, 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 quarter. That adds up to 1. Okay, so I just say like, never mind how you did it, but you managed to get your qubits A and B into this state. And now I say, then you do double clockwise. What do you get? You know, what's the new state? And just, you know, for clarity, to show you how these calculations work, I'll now solve this problem. And, you know, I'm kind of addressing here this question of like, okay, I know how double clockwise works on 0 and 1, but like, how does it work when you apply it to a state that's in superposition? And actually here it's even a little bit more subtle because like, double clockwise only operates on one qubit, but now you have two qubits in superposition. So it's like you have two particles in some weird state. And now you're doing the double clockwise operation on one of them. Like, what happens? Well, amplitude trees. Just do the amplitude trees. It's all fine. So how does it work? You just kind of like imagine, like maybe we don't exactly know how we got to this state that I said you start in, 0, 0, 0, 1, 1, 0, 1, 1. But okay, somehow you got to like this, like a hypothetical tree. Where you got to this with amplitude 0.5 and minus 0.5 and minus 0.5 and 0.5. And again, just like as if it were probabilities, like you're like, I don't know what code you did up here, but you eventually came to 0 with total probability half, and you came to 0, 1 with total probability minus 0.5. Well, that doesn't make sense because that can't be a probability, but you just imagine saying the same words, even though these are now amplitudes, and so forth. And then you just continue like the tree to see what happens. So you're like, okay, I got here, and I'm doing double clockwise on A. So all right, I have to do it for each of the four worlds. Here we are. A is 0, B is 0. B is not changing. So B will always be 0. So this is going to, we should write 0, 0, and 1, 0 here. B is just going to stay 0. And A is 0. And we know now what double clockwise does to 0. Double clockwise, if you do it to 0, you go to 0 with 0.28 and 1 with negative 0.96. So this is negative 0.96. This is 0.28. Okay, and here, kind of similar. B just stays 1 in this world. But A can go to 0 or 1. Again, A is 0, so this is going to be 0.28. This is minus 0.96. Here, B is just staying 0. But A could change to 0 or 1. Now A is 1, so you're like, okay, what happens with 1? Okay, you go to 0 with 0.96. So this is 0.96. And you go to 1 with 0.28. Okay, and last one, 0, 1, 1, 1. 1 goes to 0 with 0.96, 0.28. Okay, and now you're like, oh, it's annoying, but I gotta keep going. So I'll annoy you by doing all the details. So finally, to get the final, well, the amplitude outcomes, we do the same thing we always do. We multiply along the paths. So this is half of 0.28, so that's 0.14. This is minus 0.48, minus 0.14, positive 0.48, minus 0.48, 0.14, 0.48, 0.14. And now we're still not done because we got to do the collation. So final outcome, final state. It's going to have some amplitude on 0, 0, on 1, 0, 0, 1, 1, 0, 0, and 1, 1. Okay, and the final amplitude on 0, 0, we add 0.14 and minus 0.48, which is 0.34? No, minus 0.34. 0.34. 0, 1, that's minus 0.14 and 0.48, so that's positive 0.34. 1, 0 is 14 and minus 0.48. Yeah. Oh, this is minus. Minus 0.14 and minus 0.48, so it's minus 0.62, and this is 14 and 40, this is positive 0.62. Okay, and this is the final state. So it's kind of a pain, and there's not an intuition or anything. We just had to calculate. Okay, and if you, again, you can bust out your calculator and be like, this squared is 0.1156, 0.1156. This squared is 0.3844. This is 0.3844. And by some awesome miracle, which we'll explain shortly, this adds up to 1. Okay, so that, explains how you can, compute what happens if you somehow get to some arbitrary superposition state and then you do some composite instruction that has this definition. Any question? This is the sort of thing that you should get practice with.